The web device, when delivered through the via microcatheter, provides excellent navigability with precise deployment, making it remarkably user-friendly. When deployed with proper technique, it maintains an exceedingly low risk of intraoperative aneurysm rupture. However, the trade-off for this is a softer device that must undergo post-deployment transformation to enhance its stiffness, allowing the device to resist the impact of the inflow jet, thus preventing shape modification and compaction over time. To solve this challenge, we will have to take advantage of Nitinol's unique self-expanding properties. Thanks to its superelasticity, the device is essentially functioning as a super spring. The greater the compression, the more elastic energy the material stores and the stronger the device becomes. By intentionally oversizing the device diameter, the web is forced to undergo lateral compression upon deployment. This mechanical stress results in vertical elongation, thus improving the web's ability to resist axial loading forces. Since size selection plays a crucial role in achieving adequate lateral compression, conventional web sizing protocols are designed for wider-than-tall aneurysms only, with a height-to-weight ratio of less than 1. But when we encounter taller-than-wide morphologies with a height-to-weight ratio of greater than 1, both the manufacturer's sizing chart and +1-1 methods do not work for these aneurysms. To address this, we need to understand the universal sizing rule applicable to all aneurysm morphologies. A web device will be effective if it meets two key criteria. First, the sum of the device's height and width must equal the sum of target aneurysm's height and its diameter. Second, the device must be wider than the target aneurysm. The idea of matching the perimeters is easy to understand. When oversizing a web device in width, the height must be proportionally reduced to account for vertical elongation. Therefore, the sum of the device's height and width must always equal the sum of the aneurysm's diameter and height. As for the second criterion, the device's width must exceed the diameter of the target aneurysm to create the necessary lateral compression for secure deployment. Consider two aneurysms, one measuring 7 by 6 and another measuring 5 by 8 mm. Both have a combined height and width of 13 mm. In this case, an 8 by 5 web device can be used to treat either aneurysm, as it also has a sum of height and width of 13 mm, and its width is greater than either of them. Following the same principle, a 9 by 4 mm web device can theoretically accommodate a broad spectrum of aneurysm sizes, with varying degrees of lateral compression. However, in clinical practice, we primarily focus on the two extremes of aneurysm morphology. We recommend the +1-1 method for wider than tall and a different sizing strategy for taller than wide configurations. We will discuss how we size taller than wide aneurysms in a separate, dedicated video. Since we are sizing a 3D device based on 2D measurements only, the actual volume of the web device doesn't precisely match all potentially treatable aneurysm sizes. However, clinical experience shows this approximation remains sufficiently accurate to achieve good treatment outcomes. Take a look at this ACOM aneurysm, measuring 8.2 mm in width and 8.5 mm in height, with a near-perfect cylindrical shape, making it an excellent candidate for web embolisation. Applying the standard +1-1 rule, we will select a 9 by 7 device for optimal fit. While a 10 by 6 web could also work, potentially increasing lateral compression, it would require delivery via a via 33 microcatheter, which could add unnecessary technical complexity to the procedure. Following deployment, the device achieved instant complete occlusion, with contrast stasis in the aneurysm sac on check angiogram.